In this video, Math 0242-1342 is going to be covering sections 3.3, 4.1, and 4.2. Right here. Alex. So we completed chapters 1 and 2, and then we did a little bit of chapter 3, all up until the first review and test. So 3.3 is technically part of chapter 3, but just to try to make the sections even, it happened to land here. So 3.3, 4.1, 4.2, and then that's all we do in chapter 4 too. So then we go to chapter 5 after that, and then eventually 6. Okay, we'll start this. Okay, 3.3 is a continuation of dealing with the quartiles. I think we did, maybe we didn't do that in 3.2. So maybe this might be new to you guys. I also teach another stat class with a different book, so some of these sections are slightly different than what I'm used to. Okay, so anyway, if you take a data set, before we answer this, let me show you what's going on here. Say you have 1, 5, 10, 12, 15, 4, 5, 30, and 100. This is a data set with 7 numbers. 1, 2, 3, 4, 5, 6, 7. So there's exactly 1 in the middle. 12 is the one smack dab in the middle. And that's called the median, as we learned at the beginning of chapter 3. I know the beginning of chapter 3 was mean, median, and mode. Okay, then what you do is if there's one number in the middle, you kind of block it out and don't use it at all. And then you look at the 3 smallest numbers and the 3 biggest numbers kind of separately. If the 3 smallest numbers, 1, 5, and 10, if that was your entire data set, ask yourself what would be the median of 1, 5, and 10. It would literally be this 5 here in the middle. And this is a concept called lower quartile, lower or first quartile, Q1 for short. The lower quartile is the median of the lower half of the data. And it's also like when you break a game into 4 quarters, like a basketball game or an American football game, how you play the first quarter and then there's a commercial. The Q1's like the commercial between the first and second quarter. And then the median's like the halftime show. And then the middle of the 3 upper numbers is 30, so that's called Q3, upper quartile, or third quartile. So that's where the end of the third quarter happens, and then you play the fourth quarter after that. The median technically is Q2, but usually it doesn't go by that name very often because it already has its own name, median, that everybody's familiar with. But technically that's Q2 right there. Because you can get outliers, this 100 right here is probably an outlier because it's way bigger than all the other numbers. All the other numbers are like 1 and 5 and 10, 12, 15, 30, and then there's a big jump from 30 all the way to 100. So because outliers can greatly affect calculations, there's one called interquartile range, IQR for short, interquartile range, where you take Q3 and subtract Q1, which is what this first homework problem is asking about. And what that shows you, that's instead of doing the overall range that we learned earlier in chapter 3, the overall range is when you do 100 minus 1. There's a whole range to this data of 99 in distance, but a lot of it's distorted by this outlier, unfortunately. But if you look at Q3 minus Q1, you're getting a difference between the middle 50% of the data. So it shows you better, it's a better showing of how the middle of the data is spread out instead of the overall data, because the middle never has any outliers. If there's any outliers, they're always at the beginning or the end. So the quantity Q3 minus Q1 is known as the IQR, or the interquartile range, IQR for short. That's the first thing we do on almost every problem of section 3.3 is find the IQR. So a population has a mean of 28 and a standard deviation of 8, rounded to 2 decimal places. Find the z-score. Okay, so we'll come back to this. I'm pretty sure we're going to come back to this concept in a second. But another concept in section 3.3 is something called a z-score. In a z-score, you take whatever value that you're counting or measuring, whatever you're collecting data about. Take your value, like your test score, if you take a test, or your height, or your weight, anything that you would measure, and you subtract the mean and divide by the standard deviation. It's one of the measures that kind of uses both spread of data from section 3.2 and then the center of data from 3.1. So in this example number 2, they told me that the mean, in the paragraph it says the mean is 28 and the standard deviation sigma is 8. And just so you know this too, there's a Greek letter mu that they use for the symbol for mean. This is the Greek letter mu. It's not an English letter M. I get that a lot. And then the symbol for standard deviation is another Greek letter called sigma. And students, I don't know why this is, but they'll come to my office hours or email me, and they're like, I don't understand this R. What does this R stand for? And I'm thinking to myself, what R are you talking about? And they point at this thing, and they say, this R right here. And to me, it doesn't look anything like an R. It's more like a sideways P than an R. I don't know where they get R from, but I get that all the time. So I understand why they're struggling. Their brain is searching for something that they're familiar with, and they're probably not familiar with the Greek alphabet. But they use the Greek alphabet a lot in statistics to represent variables. If it's anything about a population, they use Greek letters. If it's about samples, then they do Roman or English letters. So they said the mean was, no, I was talking so long I forgot, I think it was 26 or 28, 28. The mean was 28 and the standard deviation is 8, so that goes after the minus and in the denominator. And then there's a number in the question. It says, find the z-score for a population value of 1. Somebody got a value of 1 on whatever you're measuring here. So they're way below average. If the average is 28 and they only got a 1, it's hard to say. We don't know what this problem's about. Is this like test scores? Is it like running ability or height or weight? Or we don't know what this is about, but it seems like 1's really far away from 28. So you subtract the top. 1 minus 28 is negative 27, and you divide by 8. Negative 27 divided by 8 is negative 3.375. Usually they like 2 decimals, but I better check and see what they want exactly. Yeah, see how it says round to 2 decimal places. Z-scores are almost always rounded to 2 places. So negative 3.375 would bump up to 3.8 because there's a 5 here. So you got to add 1 to the 7 and make it an 8. Now, I'm thinking, I thought we did do remember when we did the empirical rule? I had to think for a second if you guys have covered that. The empirical rule, remember how you put the mean in the middle? And then you add 8, add 8, add 8. Remember that? And then you go back to the mean, subtract 8, and subtract 8. These are the raw scores. These are whatever the measurement is about, like test scores or heights or weights or whatever. These are the raw scores. But the mean, remember how we would put 0 below the mean, and then it was +1, +2, +3, -1, -2, -3. These are z-scores, what you're learning right now. These are called z-scores. Z-scores are how many places, how many standard deviations from the mean are you? Somebody who's a negative 3.38 is way down here. 1's way below 4, but this is a negative 3.38 z-score. By the empirical rule, if you remember the empirical rule, 99.7% of the time you land within 3 places of the mean. 99.7%. Remember, in the homework it would say almost all of it. 68% of the time you're within the first place, then 95 is the second place out, and the third place is 99.7. So almost every z-score is between +3 and -3. Only a few are beyond that. And here's one that is. This -3, this is an exceptionally low score because it's past -3. And this was just about calculating it though, but there may, see how there's 3 parts. They may make me do this twice, but there may be a third question about, are any of these like unusual or anything like that? This is very unusual. Oh, I was going to say something I couldn't think for a second, but z-scores can be negative. Some people are bothered by this negative answer here because there's times where you can't get negative answers, like standard deviation can never be negative, or when we get to the next chapter, probability can never be negative. But z-scores can be negative. In fact, they're literally negative half the time because they're centered at 0, and 50% of the graph goes to the right of 0 and 50% goes to the left. So literally 50% of the time, z-scores are negative. So don't let a negative z-score bother you. Now, here's somebody else who got a score of 12. So how do they compare to their peer? Then you redo this calculation with 12 now. So if I put a 12 here instead of a 1, 12 minus 28 is -16, and -16 divided by 8 is -2 exactly. So this second person has a -2 z-score. Anytime your z-score is negative, that means you're below average, and obviously we don't want to be below average or negative. But if they're both negative, then one of these is better than the other. It's better to be -2 than it is to be -3. You're higher up on the scale. See, -2 is 12 exactly. 12 has a z-score of -2. But when we did this in chapter 2 with the empirical rule, or maybe it was the beginning of chapter 3, we could only do -3 exactly, -2 exactly, -1 exactly. They had to be exact ones only. Now you can do the ones that are not exact. You can still get ones that are exact, but it's okay if they're not exactly 1 or exactly 2 or exactly 3. Okay, so part 3 says, what number has a z-score of -0.5? So you're still working this formula, but the point is now we want to find the value if we know the answer is -0.5, which is still below average, but it's better than those other two. So you're basically working the same formula. It's just the unknown is in a different slot. Usually the unknown's in the answer slot, but now we know the answer and we got to figure out where this 1 or this 12 was. So the z-score is the value or the number that you get in whatever is being counted or measured minus the mean divided by the standard deviation. And it's still the same problem, so the mean's still 28 and the standard deviation is still 8. They always have to tell you those two. And then we know the z-score is -0.5, and we don't know the value, so I'll just call that x. Usually the raw scores are called x. And then it just takes some algebra to solve for this. So you can multiply both sides by 8. 8 times -0.5 is -4. And then add 28. And the raw score would be -4 plus 28, which is 24. And this will make sense because -0.5 is literally between -1 and 0. It's halfway in between -1 and 0. And look at the raw scores. That means you're halfway between 20 and 28. And halfway between 20 and 28 is 24. So that answer actually makes sense right there. Now, if they give me -0.4 or -0.6, then I wouldn't be able to tell that so easily. So this formula, if you do this works every time. But sometimes if you get exact ones or ones that are halfway in between, you might be able to tell what the answer is without doing that formula. So somebody who has a 24, they're still below average because the average is 28. But at least they're closer to average than these other two people that are even more negative than they are. Okay, find the first and third quartiles. Now, you can do this by hand and write every number down, but you'd have to put them all in order first. Then find your median, and then don't use the median if it's one number in the data set. Sometimes there's an even amount of numbers like this. Let me show you another example. Say you have 1, 2, 3, 4. Well, now there's not one number in the middle, there's 2 in the middle. So then you average that to get the median. The median would be halfway between 2 and 3, which is 2.5. And of course, we're not going to use that in finding the quartiles because it's not even one of the original numbers. You never use the median to find quartiles. But sometimes the median is one of the numbers in the data set, like this 12 was. If it is a number in the data set, draw a line on both sides and don't use it. But if it's just a number you're getting an average of, then draw the line in the middle. And you're still not using 2.5, but I am going to use 2 and 3, though, to find quartiles. And then when you get to each half, there may be exactly 1 in the middle, or there may be 2 in the middle. So here there's technically 2 in the middle, because that's the whole lower half. So the lower quartile would be 1.5. And then the middle of 3 and 4 is 3.5, so that would be the upper quartile. And then I could do the IQR. The IQR interquartile range is Q3. Yeah, I wrote that. It just looks like a 2, but this is a 3 right here. Q3, 3.5 minus Q1, 1.5. If you're looking for the IQR, you don't use the median to calculate it, but you have to know where the median is to find the other two. So this would have an IQR of 2. So if you want to do a problem like number 3 here, you can do this by hand if you want. Write every number down in a long line in order from lowest to highest. Find the median. It'll either be 1 or 2 numbers in the middle. Here it'll actually be 2 in the middle because I can tell there's an even amount of numbers here. And then draw a line right down the middle and then use all the there'll be 2, 4, 6, 8, 10 lower numbers and 10 bigger numbers. So you're going to use every number to find the quartiles here because there's 2 numbers in the middle for the median. And then there's 2 numbers for both halves too because 10 numbers is an even amount of numbers. So this example, would, if you did it by hand, would actually work exactly like the one I did, just it would be longer. Or you don't have to do this by hand. So I'm going to show you now this TI-8384. It actually helps us start using this from this point on, which is another reason why I moved 3.3 into this unit instead of in the previous unit. So it's not absolutely required to get one of these, but if you read in the textbook at all, you'll notice the textbook goes way out of their way to constantly show how to use this graphing calculator. And it's something I use in every stat class I teach. The course of statistics itself, when I was in college, it was all pencil and paper, number crunching, and you maybe had a simple calculator, but it was more about doing calculations back then. Now it's completely switched to letting technology do the calculations and you do more of the analyzing and concluding. So in all these videos going forward, there's going to be shortcuts to almost everything we do from this point on, the end of chapter 3 all the way to the end of the semester. You can do almost everything in this graphing calculator. So if you don't have a calculator yet, I would highly advise to get a TI-83 or 84. It would work with an 83 or an 84. You can have this plus edition or there's silver editions, and they have extra bells and whistles, but just a simple 83 or 84 would be good enough. If you have another calculator, say you have a TI-86 or 89 or a larger one, you can use it, but the problem is it doesn't do all the statistical things that we do. Or some people have other companies like Casio, or they just have like a dollar store calculator. You can use any normal calculator as long as it's battery operated and not connected to the internet in any way. So if it's like on a phone or a computer, that wouldn't be allowed, but anything that's handheld you can use with batteries inside of it and no internet connection. So you can use another calculator if you don't want the expense of buying one of these fancy ones, but this helps so much. You're going to see throughout the whole rest of the textbook, I'm going to show you how to do this much faster this way. And many students would rather get a good grade on their tests and take the hit on the money a little bit. If this is your last math class ever, then maybe you don't want to spend another $75 to $100 for one of these calculators. But if you're taking more math, then it would definitely be a good investment because this could be used in almost any math class. So if you want to enter data, there's a button called Stat, which is nice because that's what our class is called, statistics. Press Stat, and then you want to go into edit mode, which is the default. So you press Enter, which is like equals. You press that to go into this spreadsheet. So I can type this data in completely out of order, and the calculator can handle it out of order. So I'm just going to go across like I'm reading a book and do 3, 6, 4, 18. So you press 3, enter, 6, enter, 4, enter, 18, enter, 3, enter, 6, enter, 4, enter, 26. Just keep hitting enter after each number. 4, 7. See, there's 10 numbers already. The first row has 10 numbers. Now, keep going. This is not two separate datas. They just didn't have room to put it all in one line. So 5, 13, 4, 7, 6, 4, 4, 9, 6, 6. 20 numbers. Okay, if you go to Stat, after you put the data in, press Stat again. And we just did Edit, but if you go over here to where it says Calculate, the very first choice says 1 var stats. Press Enter to select that. Now, there are some differences in calculators. This one is an older version, so often when I choose something, it takes me back to the main screen. You might have a separate screen. If you have a newer version, there's a separate screen that's a little more user-friendly. So there, it might say something like list L1 and then paste or something like that. But just leave the default as it is and then go all the way down and hit paste and then press enter. And you get a bunch of calculations here like X bar, that's the sample mean. SX is sample standard deviation. Sigma X is population standard deviation. N equals 20, that's your sample size. Notice there's an arrow pointing down, so if you down arrow 1, 2, 3, 4, 5 times, that's as far as it goes down. This is called the 5-number summary when you have the minimum value 3, the maximum value 26, the lower quartiles 4, the upper quartiles 7, and the median 6. So now I can answer this question easily. The first quartile is Q1 is 4. The third quartile was 7. See, now I didn't have to spend a long time putting the data in order myself and doing it all by hand. The IQR, that the calculator does not spit that answer out, but that's a simple rule you should know. It's Q3 minus Q1. 7 minus 4 is 3. That's easy after you get part 1 done. Now, find the upper and lower outlier boundaries. Okay. Okay, so it turns out if you want to know, remember how we were kind of guessing if we had outliers like this? I said this might be an outlier right here. Here comes a definitive way to tell if you have an outlier or not. So you do your IQR. I just got 3 for the IQR. Right there, 3. If they just ask for IQR, that's it. If they want to know about outliers, you're going to do another step to this IQR. Take the IQR and multiply by 1.5. It's a little weird. Why is it 1.5? But that's the rule. You multiply by 1.5. 1.5 times 3 is 4.5. And then remember Q1 was 4 and Q3 was 7. So once you get 1.5 times the IQR, this is an amount that you add to the upper quartile. And you subtract it from the lower. So these are what are called the boundaries. 4 minus, this is, I was writing this weird, but this is supposed to be a 4 right here. 4 minus 4.5 is negative 0.5. You must be, if you're a data number in my data set, all these data that I collected, you must be smaller than that. If you're smaller than negative a half, you're an outlier. So what I'm doing is I'm calculating the lower limit, the lower boundary. Anything past that's an outlier. And then if you add 7 plus 4.5, you get 11.5. You must be bigger. Remember at the carnival where they have roller coasters and they have that little poster and it says you must be this tall to ride this ride? That's exactly what's happening here. You must be this tall to ride this ride. If you're bigger than this, you can't go on the ride and you're an outlier. Or if you're smaller than this, you can't go on it. So anything smaller than negative a half is an outlier, and we don't even have any negatives, so there's no outliers on that side. And anything bigger than 11.5 is an outlier. And there is some numbers bigger than 11.5. There's a 13, there's an 18, and there's a 26. All three of those are outliers. You can get multiple outliers. And you can have them on the lower side and the upper side, or only on one side, 13, 18, and 26. There's no way to definitively tell if you have an outlier without doing this calculation. So first you get your quartiles, then you find the IQR, then you multiply the IQR by 1.5, and then you add that amount to the upper quartile and subtract it from the lower. Anything past those two are considered outliers. Okay, here's some more about z-scores again. So there was some kind of music theory class that had an average score. The mean score was 79.3 and the standard deviation was 6.3. And somebody in that class, yeah, that was, I was checking if this, because it said music theory and then down here it only said theory. Somebody in that class got a 70 on their test. So they're below average because the average is 79.3. But what's their z-score? So for the music theory, which we just call this Z1, the person got a 70. That's their actual value. The average was 79.3. And the standard deviation was 6.3. And I'll just pull up the simple calculator here because it'll go quicker. 70 minus 79.3 is negative 9.3. Divided by this 6.3. Divided by 6.3 is negative 1.48. Remember, we round these to two decimals, negative 1.48. But then somebody's in another class that has a totally different test. So when you have different tests, like the SAT versus the ACT, you can't just say the one with the higher score is better because they're often graded on different scales. 800 on the SAT, how can I tell if that's better or worse than a 27 on the ACT? The lowest possible SAT score is bigger than the highest possible ACT score. So when things are on different scales, it's not a fair comparison just to say that 70 is better than whatever the other one is. This one's negative 1.48. So the other class, their average score was lower. This class averaged 79 on their test. This one only averaged 69. It's a harder test. It might be a harder class and a harder test. So you can't just say that a 70 is better or worse than an 80 automatically. The only way to compare them is z-scores. Now, clearly this one's better because this person's above the average of the class where the other person was below average, but sometimes it's too close to call. So 80 minus 69.3 divided by this 6.6 right up there. And this is going to be positive, so clearly it's better. 80 minus 69.3 is 10.7 divided by 6.6. They're positive 1.62. So who's relatively better? It's not who has the better actual score. The second one's definitely better actually. 80 is better than 70. But sometimes the one with the better actual score has a lower z-score. But here it's actually still the higher one. But the lower actual score can have the higher z-score, and then we say it's relatively better. A 27 on the ACT might be better than an 800 on the SAT. So this one was 1.62. This is probably not the best example to see this for the first time because clearly the 80 was better without even doing z-scores. But which score is higher relative to the population of scores? It's the second one. And not because 80 is better than 70, but because 1.62 is better than negative 1.48. Kolbe's theory score had a z-score of 2.31. What was his theory score? Okay, so this is that working backwards again. So what if you know the z-score? What if the z-score is 2.31? What is his actual score? X. And the theory was the first class, so the average is 79.3. And the standard deviation was 6.3, if I remember right. Yeah, 6.3. So this is one where you just do a little bit of algebra. Multiply both sides by 6.3. .3 times 2.31 is 14.553. And then add this 79.3. So his actual score is 93.853, and then where do they want it rounded? Round to 2 decimals. 93.85, because the next number is a 3, so you don't add 1. 93.85. And same thing for this other person. They have a z-score of 1.3, and they were in the other class performance, Maya. So Maya got a 1.3 z-score. What's her actual score? She got a 1.3 z-score. What's her x? This is kind of like x1 and x2 then. Her class had an average of 80. It was, or an average of 69.3. So her test was easier because the average was lower. I mean, her test was harder because the average was lower. And then her class had a 6.6 standard deviation. So multiply both sides by 6.6. .6 times 1.3 is 8.58. And then because it's minus 69.3, you want to add 69.3 to both sides. If we add 69.3 to both sides, this will cancel out and get x by itself. So take this 8.58 and add 69.3. 3, yeah. So there's nothing around here because it's exactly 77.88. So there's nothing interesting about these last two parts, but they're just making me do that again to show you that you can know the actual score and find the z-score, or you can know the z-score and find the actual score. Either way. Okay, here we go again with the quartiles, but they did the first part for you. So Q1 is 31. That's the lower quartile. Notice they do write it as Q2 this time, but that's the median. And then Q3 is 47. So part 1, find the IQR. That would be Q3 minus Q1. You don't use Q2 to find the IQR. So Q3 is 47 minus Q1, which is 31. She or he, no, I don't even know if this is a single person, but the IQR is 16, the interquartile range. Find the upper and lower outlier boundaries. So if they ask for the IQR, it's just Q3 minus Q1. But then if you do 1.5 times the IQR, then you get the amount to add and subtract to find the boundaries. So 1.5 times 16 is 24. The upper quartile was 47. You always add this amount to the upper quartile. 60, 71. You must be bigger than 71 to be an outlier. You have to be this tall to ride this ride at the amusement park. You have to be bigger than 71. That's the upper outlier boundary. Anything bigger than 71 is an outlier. And then you take the lower quartile, which was 31. And in this problem, they just told me what those two were. The other problem, I had to find them myself. And now you minus this 24. It's always upper plus and lower minus. So 31 minus 24 is 7. You have to be smaller than 7 to be an outlier. Now here, they're not showing me the original data, so I can't check is there any outliers or not, unless they're going to do that in the next part. But the lower outlier boundary is 7. The upper outlier boundary is 71. A population size greater than 53 be considered high? Would a population size of 53 be an outlier? So they're just saying that whatever, it would maybe help if they showed us the data, but apparently they're looking at the data and somebody thinks, 53 seems kind of high compared to the other numbers. Is it really an outlier? Just because it seems high doesn't guarantee it's an outlier. You could guess maybe this is an outlier, but definitely it's not, because we just figured out that you have to be bigger than 71 to be an outlier, and 53 is not bigger than 71, so 53 would not be an outlier. Even if it remember that problem where I jumped from 30 to 100? That one probably is an outlier, but you really can't tell for sure until you make this calculation. And sometimes it seems like, oh, that seems like an outlier, and then you go do the calculation and it misses out by a little bit. Now, in case you're curious, why is it 1.5? That seems like a weird amount. When I was learning how to teach this class, the professor we had said that he used to teach high school statistics, and his students always asked him, why is it 1.5? That's a weird amount. He didn't know either. And he was at a workshop later that the guy that invented this calculation, there's a guy who invented this 5-number summary, and there's even a thing called a box plot you can draw from it. He's the one that came up with the rule. So he asked this guy, he's like, my students always ask me, why is it 1.5? This seems like a weird number to pick. And he said, well, it was just through trial and error. First he tried 1, and then the difference wasn't very big, so it was easy to catch outliers when he only had a 1 there. And he thought that problems shouldn't have a whole bunch of outliers, that they should be more special than that. So then he switched from 1 to 2 and did 2 times the IQR. And then it was such a big number, then it was way out there. It really took something extreme to be an outlier. He didn't think it should be that hard to find them. So he thought 1 was too little, 2 was too big, and he literally shrugged his shoulders and cut it in half. Halfway between 1 and 2 is 1.5. And then he did a few examples, and it seemed right, and it just stuck like that. So a lot of things in math and science, whoever discovers them or invents them gets to name them. They get to come up with the rules. And if enough people like what they're doing and follow them, then it eventually becomes a rule that everybody follows. So literally the 1.5 was just made up by somebody. Okay, is this... Oh yeah, okay, so then you can do a box plot. In fact, let me show you in the graphing calculator. Remember this data I already have in here? So I had this data in the calculator, stat and edit. We typed all those 20 numbers in. And then we went to stat, calc, 1var stats, and ran it. And then I went down to the bottom and got the 5-number summary. A box plot is a picture of the 5-number summary. The minimum value is the end of the graph, this little line that comes out. The left side of the box, these are called box plots because there's a box in the middle. The left side of the box is the lower quartile. The line somewhere inside the middle of the box is the median. The right side of the box is Q3, and then the end is the maximum unless it's an outlier. If it's an outlier, a lot of books put a circle for it. This book, I guess, is doing X's. I guess they couldn't put a circle on this graph. But see, this X is telling me, oh, that number, there's one outlier on the upper side and no outliers on the lower side. This one's got two outliers on the upper side and none on the lower side. And then these little lines are called whiskers. So some people call this a box and whisker plot. The line goes to the biggest or smallest numbers that are not outliers. So if you do have outliers, then the line doesn't go all the way to the maximum. This professor that invented the quartiles and decided that 1.5 IQR rule, he's the one that invented these graphs called box plots. So this can be very interesting if you do two of them on the same graph. Here's hospital A, hospital B. You can compare things like which one has a bigger center of data. The line in the middle is the median. So hospital B has a larger median than hospital A because it's further down the number line. So we could say hospital B has a higher average, a higher median, something like that. Which one is more spread? See, more spread, that's another aspect. Clearly, hospital B has a greater overall spread. If you do the max minus the min, that's definitely bigger for B than A. Now, if you do the interquartile range is the length of the box. And B appears to be a little bigger, but maybe not greatly bigger. It seems to be greatly bigger in overall range, but a little bit bigger in IQR. So hospital B generally has a higher daily number of patients. Oh, no, okay. So that's about the average there. This first part's about the average. Yeah, B definitely has a higher average than A. And B is also more spread out, and that doesn't have to be the case. The one with the higher average could have a smaller spread to it, actually. And you can draw a box plot in here, too. If you go to second y equals, this takes you into the stat plots. Plot 1, see how they're all turned off right now? I can go into plot 1 by pressing enter. And while it's flashing on the word on, I can turn it on. And then down arrow to the type of graph. And you guys have learned histograms so far. You haven't learned these two yet, or this first one. But the fourth one, 1, 2, 3, 4. This one's a box plot with outliers. Or you can do what's called a modified box plot. If you don't care about outliers, you could just look at that. But I would rather do this one because if there's outliers, I want to know. And remember, we actually found the outliers to this problem. It was 13, 18, and 26. So this should show up as outliers. If I choose this one, there should be 3 outliers in the graph. And leave the X list as L1, leave frequency as 1. The mark is if there's outliers, how do you want them to show up as? You want them to be squares, pluses, or dots. They're doing X's, which I don't even have an option for X. But they're technically circles, but you can pick the dot if you want to be technical, but they're hard to see. Maybe you wouldn't even notice that dot unless you have the vision of a hawk. So I just leave it on a square because it's nice and big and easily visible. And you can always change it to an X or a circle if a textbook wanted it that way. So when you want to graph one of these stat plots, you don't hit the graph button. That's what algebra does. Instead, you hit zoom and the number 9, because if you actually go down to number 9, it'll say zoom stat for statistical graphs. See, if I go down to 9, zoom stat, I'll zoom in on stat graphs, but I'll put it back up at 1 to show you that you don't have to do that. So you just hit zoom and the number 9 and it graphs it. And see, there's 3 outliers. And you can hit trace to see all the numbers. If you hit trace at the bottom, it shows you the minimum's 3. Right arrow to the lower quartile 4. Right arrow to the median 6. Right arrow to the upper quartile 7. The other whisker stops at 9 because apparently 9 is the biggest number that's not an outlier. And then 13, 18, and 26 are all outliers. So even the calculator will show you all this. This is why it's so nice to have a TI-83 or a TI-84 calculator. It can do all this stuff in fractions of a second that if somebody tried to do this by hand, it would take a half an hour, literally. And they might make mistakes, too. And then you can compare things really quickly, too, and make these conclusions. That problem, they were nice enough to tell to you, but if you don't have them telling you what the graph is, you can draw your own at least. Now here, it's really helpful to have a graphing calculator. This is an extremely painful by hand formula. If you want to do this by hand because you can't afford a graphing calculator, read the textbook and you can follow an example, and it'll take you 20 minutes to do this by hand. If you want to do it by calculator, it's so easy. So I have 2 sets of data now. Now we're in chapter 4 and there's 2 sets of data. So go to Stat and press Enter for edit. Whenever you have data previously in your list that you want to get rid of, you go up arrow to where the L1 name actually is, right where L1 is. Don't hit delete or the whole list disappears. Hit clear, enter, and that wipes out old data and you can type new data. So I'm going to type the X's in L1, 5, 27, -5. Whoops, yeah, I got it, okay. I didn't think the negative went. 39, 3, 25, and 9. Watch out for negative. This is the negative button right next to the enter button. This is subtraction. Don't hit that. If you hit subtraction when it's supposed to be negative or negative when it's supposed to be subtraction, it'll mess up in the calculator. Okay, so I just wanted to make sure there was nothing past that 9. Okay, now you go over to the second list, L2. These L's stand for list. List 1, list 2, list 3. So put all the Y's in list 2. 33, 1, 8, negative, oh no, not yet. Sorry, 4, 8. I didn't even get that. 8, 40, -10. 23 and -3. So there's a function in this calculator that is what I call the one-stop shopping for all of chapter 4. Press Stat. Remember how we went to calculate for one of our stats? Well, there's something called tests that you'll learn more about in future chapters. But go to Stat and Tests and up arrow until you get one near the bottom called LinReg T-Test. You might have more than me. If you have a newer calculator that was made in more recent, this calculator is like 10 years old, and they've made some upgrades to them. Or if you have like a silver edition, you might have other bells and whistles. But somewhere near the bottom, yours might not be the second from the bottom, but somewhere near the bottom, I went Stat, Tests, and I up arrowed to get to the bottom of the list. Otherwise, you can down arrow 15 times if you want. But mine is second from the bottom. Yours might be third or fourth from the bottom. You might have a few more things than me. LinReg T-Test is what you're looking for. It's very easy to use. Press Enter. And as long as you have X's in L1 and Y's in L2, you don't have to change anything. Always keep frequency as a 1. And just keep this on not equal to. In later chapters, you'll learn what about this less than and greater than. But for now, just keep it on not equal to. Regression equation, you can leave that blank. Literally, you just go down and hit calculate. You don't have to change anything. Go down and hit calculate. There's a bunch of numbers here, and some of these won't make sense to you until we learn more chapters. But notice the down arrow, go all the way to the bottom. There's R. R is called the correlation coefficient, and it measures how strongly 2 variables are related to each other. Round to at least 3 decimal places. So 484, and then there's a 3 after that, so 484. Correlation tells you how strongly 2 variables are related to each other, and it always ranges between -1 and +1. And then halfway in between 0. If your correlation is at or close to 0, we say there's no correlation, and that means one variable is not related to another variable in any way. Think of something like height versus IQ. Somebody's height has nothing to do with their intelligence. You can be tall or medium or short and have a high or a low intelligence. So some variables clearly are not related to each other. Height and IQ don't have anything to do with each other. But height and arm span do have something to do with each other. Generally, taller people have longer arms, so if you measure their height and measure their arm span, The taller you are, generally the bigger your arm span is, and the shorter you are, generally the shorter it is. It's not a perfect relationship, but there's a strong relationship there. So two numbers that are kind of a loose guideline, this isn't definitive, but a loose guideline are 0.5 and 0.8. If you're above 0.8, like anything between 0.8 and 1, that's called strong correlation. And that means the two variables are strongly related to each other, like height and arm span. If you're below 0.5, that's weak correlation. And ours is below 0.5, ours is 0.484. This is a weak correlation, so our variables are not really related to each other very well. And if you're anything in between, it's moderate. And the same rules happen on the negative side. It's just clearly negative when you have a negative in the calculation. Positive correlation means as one variable increases, so does the other one. People that are taller have longer arms. Negative correlation means as one variable goes up, the other one goes down. If you go higher and higher and higher up into the mountains, higher and higher altitude, the temperature generally gets colder and colder. That's a negative correlation. The calculation will tell you if it's positive or negative. If you go up down to this R, if it's negative, you'll see the negative there. So the positive negative doesn't bother people, but just knowing roughly where you're at. Is this a strong correlation? Is it moderate? Is it weak? Now, there is a scatter plot in here. If I go to second y equals, go into plot 1 again by pressing enter. Remember how we did box plot a second ago? The very first type of graph is called a scatter plot. This is a scatter plot right here. It's kind of like the first quadrant of an algebra XY axis. So if I press enter on type of graph, on this very first type, it changes me to a scatter plot. And notice I don't have to change anything else. So zoom 9. Zoom 9 is always a way to draw statistical graphs. And what you're hoping happens is you want the points to be lined up as much as possible. And you're hoping that there's either a positive or a negative trend left or right. You don't want it to be horizontal left or right, and you definitely don't want what they're doing here. This is a made-up graph over here. You don't want a curved graph like this. Curved is very bad. Curved means your correlation is close to 0. So the correlation coefficient here is not appropriate because this is not a strong correlation. It's not linear enough. There's either a weak linear or no linear relationship. It's a non-linear because it's curved. We only deal with linear relationships in this 1342 class. If you take higher levels of statistics, like at a 4-year university, they would do curved ones, but we don't do any curved ones. So you can draw your own scatter plot. Mine's different than theirs because they didn't tell me the data. This is from the previous problem. But you can just draw a scatter plot, and this one's maybe, this is hard to tell how good this one is, but actually we know what it is because I did the correlation already. It's got a weak correlation. And that's why when I hit zoom 9, this is not perfectly lined up. If my whole data were just these 4 points, that would be really lined up pretty well. But there's 2 offline this way, and there's one kind of hiding there. From the main line, there's points above it to the upper left, and then below it to the lower right. That's bad. You want them lined up. You don't want them spread out like that. So the more spread out it is sideways, the more likely you're going to drop from strong to moderate to weak. Weak correlation, you almost never use weak correlation to make conclusions from. Okay, see, they want me to do a scatter plot. And I guess I got to do this one manually. I can do it in my calculator too, but it won't help me for this. So where the dozen eggs are $1.67, the milk's $3.43. So you want to go to 167 on the x-axis, and then up to 343, which would be halfway between 42 and 44. And you just click that, and it puts a point there. Then do 194 and 352. 194, 352. It's real sensitive to it. It slides on me real easily. 196, 347. Right there. 177, 358. Oops, I missed that one, I think. Let me erase that one. Needs to be right there. This one's hard to see because once you go up, you can't see the 177 anymore. Right there, I think I got it now. Yeah, see, it's one past 176. 177, 180 and 347. 180, 347. 188, 354. 183, 358. And finally 165, 343. So see this here? This is generally going upward, up to the right. That's positive correlation, but there's a wide spread sideways, so this is probably not very strong correlation. So there's the scatter plot. It almost looks like a parachute here, or a mushroom. Compute the correlation coefficient. So the best way to do that is put this in the graphing calculator and let it do it for you. Otherwise, it takes 20 minutes by hand. So stat, edit, go up to the top and hit clear enter from the old data. Up to the top, clear enter. Type all the eggs in L1, 1.67, 1.94, 1.96, 1.77, 1.80, 1.88, 1.83, and 1.65. Now go over to L2 and put all the milk numbers, 3.43, 3.52, 3.47, 3.58, 3.47. Watch out for typos too, otherwise it'll be wrong, but 3.54. If you were taking a test, maybe after you type them all in, go back and double check them all. 3.58, 3.43. There should be an equal amount of numbers in each list too. So they both end at the same time. You can hit zoom 9 right away and it'll draw a new scatter plot. See, here's this parachute or mushroom shape that we just had. You can look at this. It won't help you do part 1 because you got to click these exactly, but at least you can see the shape by hitting zoom 9. Okay, so now do stat, test, up arrow to the linreg t-test. And just go straight down and hit calculate every time. And go straight to the bottom. See, this is a pretty weak correlation, 418. It's below 0.5, and I could kind of suspect that because this was so wide this way. If these points lined up like this, or even like that, this could be okay. These 5 points are pretty lined up, but then you got these 3 that are the wrong way. So that made the correlation drop down below the 0.5 level that's into the weak range. In a month where price of eggs is above average, what would you expect the price of milk? Would you expect the price of milk to be above average or below average? Well, this is a positive, even though it's a weak correlation, it's positive. So when correlation is positive, as one variable increases, so does the other one. So if milk is above, if eggs are above average, then milk should also be above average. It's just you're not going to predict it very accurately because it's a weak correlation. But it should be above, milk should be above average since R is positive. When there's a positive correlation, they both go in the same direction. When there's a negative, they go in opposite directions. Which of the following is the best interpretation of the correlation? Now, one thing about correlation is you never want to say cause and effect. Even if you have a very, very strong positive correlation or a very strong negative, you can't say that one of them is causing the other. The correlation has nothing to do with cause and effect. So as soon as they say causes, those are out automatically. So changes in the price of eggs or milk do not cause the change in the other one, but the correlation indicates that they go up and down together. There's a relationship, and we can predict sometimes what will happen. If our correlation's strong or possibly moderate, we can make good predictions, but we can never say cause and effect no matter how strong it is. That's a danger to watch out for. That's why they put this last part here. Okay, so we're getting probably towards the end of 4.1 already. In a survey of sales data from recent summer, it is discovered that there is a positive correlation between ice cream and sales of sunglasses. Do you believe that purchasing ice cream causes somebody to want to buy sunglasses? See, you don't want to say cause and effect. Ice cream has nothing to do with sunglasses. What's causing these things is a third outside variable. When it gets hot outside, temperatures. When temperatures increase, people eat more ice cream and people need sunglasses because the sun's out stronger and longer. So purchasing ice cream does not cause you to want to buy sunglasses because correlation does not imply causation. You can't talk about cause and effect no matter how strong it is. But if there's a strong correlation, you can, and if you tell me, oh, ice cream sales just increased by 50%, then I might be able to predict that sunglasses went up by 50% too. It's just that the one thing is not directly causing the other. Okay, so that is the end of 4.1. I can tell that there because we're done with correlation. Now this is the next concept when you're doing a regression line. That's section 4.2. So this is a good stopping point. Let me give you the next magic word. And we had last chapters, we had this theme of cities around Texas. So I'll do a different theme this time. The magic word today is going to be rockets. The magic word is the Houston Rockets. So that's your first of 5. There's going to be 5 more videos this unit for the second test, and then you'll get 5 magic words. And now that you know what the first one is, you might be able to guess some of the other ones, but at least you won't know the order of them unless you watch the videos. Okay, here, this is, again, remember I said one-stop shopping. So go to Stat and Edit. And I can't tell if you can see all that or not. There. Okay, so go up to the top and hit Clear Enter. Trying to get this so you can see it all at once. There, that's better. Clear Enter. Clear Enter at the top. Type the X's in L1, and at least this is not a painful list to type. 2, 7, 6, Enter, 3, Enter, 4, Enter. Don't try to sort them either. Keep them in the order they are. 4, Enter, 6, Enter, 5, Enter, 3, Enter, and 2, Enter. Stat, Test, Linreg, T-Test. This is your one-stop shopping. It does everything in Chapter 4. Go down to Calculate. Now, Section 4.1 is going all the way to the bottom and getting this R value. Notice I got a larger one this time, 686. That's at least in the moderate range, between 0.5 and 0.8. At least it's not weak. But go back up to the top for a second. You see at the very top it says y equals a plus bx. In algebra, you probably remember y equals mx plus b. This is the most famous equation in algebra. It's the equation of a line. Stat calls it a plus bx for some reason. They do it differently. The number in front of x is the slope. The other number is the y-intercept. Well, in stat, the y-intercept is the a and b is the slope. So it's backwards and a little confusing, but it's really the same thing. And the calculator makes this so easy, you don't even have to worry about it. So all we need, and they put this hat, see this hat on top of the y? The regular y is the actual y, but the little hat on top of the y means you're doing a predicted y. So you don't have to worry about that because it does it for you, but this is predicted y equals a plus bx. I need to plug in a and b, and there's a right there. Round to 4 decimals. Round the slope and the y-intercept to 4 decimals. A is the y-intercept, 1.697, bump this up to a 7 right here, 1.6977. And then plus, now you plug B in. You can't forget the format, it's right up here, y equals A plus bx. And B is the next one down. You just can't see it until you down arrow. 0.5232, but there's a 5 after that, 5233. 5233, and then you just put x at the end because it's the equation of a line. And then if your correlation's strong enough, maybe this moderate one's not strong enough, but if you get strong enough correlation, then you can make predictions. This one's not asking me to make a prediction, probably because it's only moderate correlation. So yeah, they just wanted you to see how to calculate that. See, this is very painful to do by hand. But it's, other than the fact that this data is really long, this is not too bad with the calculator. So unfortunately, this one's got messy data to work with, but I'll clear out my lists. Put all the egg prices into L1, 113, 116, 119, 114. There's two different 117s, but put them both in. 128, 126, 128, 135. Now put the milk prices in the second list. 323, 323. This must be from long ago because we know prices are much higher than this now. 321, especially the egg prices. 312. 309, 314, 313, 317, 321, and 324. Whoops, I didn't get the decimal. Almost had a typo. Okay, so let's run it again. Stat, test, linreg, t-test. Straight down and calculate. Okay, they want the least, this is called the regression line, or it's sometimes called the least squares regression line. But it's just literally a plus bx, what your calculator is spitting out. Here's the a, 2.9579, make that a 9, 2.5979. 2.5979. Oh, I had a dyslexia moment. 2.95, not 59. 9579 plus, and then down here to see the B, 0.1807, make that a 7, 1807. And then you put x at the end. So that's your y-intercept and your slope of this line. If the price of eggs differs by 15 cents from one month to the next, how much would you expect the price of milk to differ? So what that means is plug 0.15 in for x, because eggs are the x's. So take your equation, 2.9579 plus 0.1807, and multiply by, whoops, I didn't get the 8 there, 1.807 times whatever x, they're giving you an x value, you just multiply by whatever x they give you, 0.15. So milk should then be $2.99 if you want dollars and cents. $2.99. 2 decimal places because they're doing money. Okay, what happened there? 2.995. Oh, I missed. I didn't get a 7 in there. I typed it wrong. 2.97. I missed the 7. See, watch out for typos. It's real easy. You don't even know you do them, unfortunately, a lot of the times. And that's enough to count it wrong, too. Times 0.15. See, that's better. 3, because all the prices were in the $3. So $3 exactly, although it was only off by a penny. 2 decimal places. If the egg price differs by, okay, maybe that's what they're talking about. 15 cents. Okay, so it's not 15 cents. We need... the reason it's not 15 is because it's saying differs. That's the difference here. See how these prices are not... They're not 15 cents. No, the eggs never cost 15 cents. So what do they mean by differs is what's troubling me right now. If the price of eggs differs by... That means it could go up or down that much. Whenever you get stuck like this, sometimes you just either get it wrong or go over to this help where it says example on the side. And see how they're showing you how to do this by the calculator. Okay, so price of egg differs by 35. So they're multiplying the slope by the difference, 7 cents. Okay. Predict the price. Okay, yeah, see, I was doing what part C wants. Okay, so close this. So apparently all you do is take your slope, 0.1805, or 1807, multiply by 0.15, and then round to 2 decimals. So if milk changes by 15 cents, I would expect I said that backwards. If eggs change by 15 cents, I would expect milk to change by 3 cents. And the reason you only use slope is rise over run, and that's where the change is actually happening. The y-intercept is where it's just a starting point, but then the slope is what it's changing by. So that's what that word differs was trying to infer, is that you just want to work with the slope only for that one. So if eggs go up 15 cents, I would expect milk to go up 3 cents. See, there it was right. And now here's what I was doing. It says predict the price of milk if the egg price is $1.82. See, when you're predicting it, you should get a number that's close to all the X values. If the milk goes all the way, if the eggs go all the way up to $1.82 from high inflation here and compared to these prices, what would the milk be that month? So that's what I was doing previously. 2.9759 plus 1.8 or 0.1807 times $1.82. And see how you get a price that's similar to all the milk prices, $3.30. So for part 2, you only multiply the number they give you by the slope, but in part 3, you do the whole equation. That's the difference there. Okay, 12's correct now. Okay, this looks like the same kind of problem. Now, they ran out of room here, apparently. Systolic, there's 2 columns for that, but put all of that into L1. So I'm going to put 115, 113, 123, 119, whoops, and 118. But keep going because, whoops, I hope it doesn't blow it. Whoops, I didn't want that. Okay, I'll just have to do it this way. 130. I was trying to get it so I could see it at the same time. Maybe I can make this smaller. There, 130, 116, 133, 112, and 107. So you're putting the entire first and third columns into L1 because they're both labeled systolic. Then diastolic, that goes in L2. So 83, 277s, 69 and 88, slide over here. Here's more diastolic here, 76, 70, 91, 75, and 71, and there should be a same amount of numbers in each column. Yes. Okay, they want the linear regression line, stat, test, up arrow to the linreg t-test, go down and hit calculate, and look for the A and the B. The A is already visible, down arrow wants to see B. So the equation is going to be 4 decimals, 25.1552. Make this one become a 2 because of the 8. 25.1552 plus, now grab the B, 4430 x. Is it possible to interpret the y-intercept? Okay, the y-intercept is this 25 number. And what it represents is, it represents the whatever the y is about, diastolic. It's your diastolic amount if the systolic was 0. So if that part of your blood pressure was 0, that's what your other blood pressure number would be. So sometimes it's possible to interpret it, but often it's not possible because, say you're doing like height versus IQ. If somebody has a 0 height, their IQ would be whatever. How can you have an IQ of anything if you have 0 height? If you have 0 height, you don't even exist. So sometimes a 0x is meaningless. So it may not be possible to do this because the x values are all positive. There isn't an x that's 0. If somebody had a 0 blood pressure, they'd be dead. So then you can't really interpret that. A lot of times that's the case where the y-intercept doesn't make any sense. But it's a natural result of drawing diagonal lines in algebra is why it comes up. If the systolic pressures of 2 patients differ by 12, how much would you predict their diastolic pressures to differ? See, here's this differ one again. So that means you only multiply the 12 by the slope. I'll do it here in the simpler calculator. Take the slope 44.4430 and multiply by 12. If you want to do this differs, I'd never heard of that before, but differs, you just multiply the slope by the number they give you. And let's see where they want it rounded. Round to 3, and it came out to exactly 3. So 5.316. Predict. Now, when you're making a prediction, then you use the whole equation. So predict the diastolic pressure when they have 137 for their systolic. So now you go to this equation and put the 137 right there. So 0.4430 times 137 plus 25.1552 and round to 1 decimal place, so 85.8. And in this simpler calculator, I did the multiplying first just to follow order of operations. But in the graphing calculator, you could actually do that all just like it is. You could do 25.1552 plus 0.4430 times, I think it was 137. See, 85.8 that way. So I could have just done it in the better calculator, but okay, these last two problems are reading data from the calculator or from computer technology. So see, they ran the linreg t-test for us, and here's the A, here's the B, here's the R. We didn't learn about R squared, but that's okay for now. So they want the regression line. Well, that's easy if I have A and B. It says do not round your answer, so type the whole thing. 1.79582874, that's A. Plus B is 0.3993661, and then you put an X at the end. The equation's right above it right there. So they did the linreg t-test for you. They just wanted you to read the technology. because they know not everybody has this calculator too. So in case you don't have it, then you can do problems like this. What is the correlation? Correlations are, so the correlation is, I guess they don't want it rounded, 6.5373916. But 6.5, that's in the moderate range because it's between 0.5 and 0.8. Predict the price when the prime interest rate is 7%. So that would mean, see, the prime interest rate is X in a percentage. So put the percent right in there. Put 7 right in for X. $1.795828874 plus 0.39936061 times the 7%, but leave it as a percentage. Don't make it a decimal. It said 7% here, and this shows percent, so then that means they want you to leave it alone. Round to 4 decimals, 4.5914. Okay, and finally, I think this is another one of reading technology. Okay, intercept, that's the y-intercept, and then this is the slope. So remember, in the least squares line, you put the y-intercept first, 3.966825575, plus the slope, 0.83695567, and then an x. Predict. Whenever they ask you to predict, you're going to use the whole equation, and you got to plug something in for x. Usually it's this number they're giving you right here. So plug in, well, let me do it on the better calculator. Type 3.966825575 plus 0.0836957 times this 330 they're giving me. And round to 3 decimals. 31.586, and there's a 3 after that, so leave it 31.586. So anytime it says predict, you use the whole equation. If it says differs, then you only multiply by the slope. And now we've done all 15 problems up here at the top. It's all green along the top. So we've done every problem, all 15, in sections 3.3, 4.1, and 4.2. Which is the first of, if you don't count the 0242 homeworks, there's a 3.3, there's this one, 2, 3, 4. There's 4 of them plus a review. So again, it's just going to be like the first unit. 4 regular 1342 assignments and a review. There'll be 5 videos. Each one will have its own magic word. And now you've got the first one out of the way. And this video was just under an hour and a half, similar to how in-person classes last, so that was pretty good timing. That is the end of the first of 5 videos for Unit 2.